There is a planet in our solar system so large, so violent, and so incomprehensibly powerful that if you fell into it, you would not simply die, you would be erased. Layer by layer, pressure by pressure, atom by atom, until there was nothing left of you. Nothing left of your spacecraft, nothing left of any evidence that you ever existed at all. That planet is Jupiter. And what happens inside it is not just deadly, it is the closest thing to pure, measurable, scientific hell that our solar system has to offer. Jupiter is the largest planet in our solar system, so large that every other planet, including Saturn, Uranus, and Neptune, could fit inside it simultaneously, and there would still be room left over. It contains more than twice the mass of all other planets in the solar system combined. From Earth, it looks like a bright, steady light in the night sky, almost beautiful, almost calm. But that appearance is a complete illusion. Because Jupiter does not have a surface, there is no ground to land on, no rock to stand on, no solid place where anything ends or begins. Jupiter is a world made almost entirely of gas and liquid, and if you fell into it, you would fall for a very, very long time, experiencing conditions that escalate from merely unsurvivable to something that has no accurate human comparison. And recent data from NASA's Juno spacecraft, combined with new atmospheric modeling completed in 2024, has revealed that Jupiter's interior is even more extreme than our previous worst-case estimates suggested. What we found changes the picture entirely. Understanding Jupiter matters in ways that go far beyond simple curiosity, because Jupiter is not just a planet, it is a shield, a gatekeeper, and potentially the reason complex life exists on Earth at all. Its enormous gravitational field has spent billions of years pulling in asteroids and comets that would otherwise have bombarded the inner solar system. Scientists estimate that without Jupiter's gravitational influence, Earth would experience catastrophic asteroid impacts roughly 1,000 times more frequently than it does today. Jupiter also represents the boundary between the rocky inner planets and the frozen outer solar system, and understanding how it formed and what it contains is directly connected to understanding how Earth itself became habitable. Beyond that, Jupiter's extreme internal conditions mirrored what scientists believe exists inside gas giant exoplanets, worlds orbiting other stars throughout the galaxy. Every measurement we take of Jupiter is data that applies to thousands of other worlds we may never physically reach. To understand what falling into Jupiter would actually mean, you need to understand its structure and why that structure makes it unlike anything else we have ever studied. Jupiter's atmosphere begins where its faint ring system ends, and from that point downward, it descends through layers of increasing pressure, increasing temperature, and increasingly alien chemistry for tens of thousands of kilometers. The outer cloud layers, the bands of orange, white, and brown you see in photographs, are composed primarily of ammonia ice crystals and ammonium hydrosulfide, and they are being churned by wind speeds that regularly exceed 600 kilometers per hour. The Great Red Spot, Jupiter's most famous feature, is a storm that has been continuously active for at least 350 years. It is wider than Earth. It reaches deeper into the atmosphere than scientists previously understood, with Juno revealing its roots extend over 500 kilometers below the visible cloud tops. Below those outer clouds, pressure begins to build, temperature begins to rise, and the chemistry begins to do things that have no equivalent on Earth. Approximately 50 kilometers below the cloud tops, pressure has already exceeded what any submarine on Earth is built to withstand. At this depth, ammonia and water mix in proportions that create a corrosive, electrically active slurry that would destroy any known material almost instantly. Continue falling, and you reach a layer where water ice transforms into liquid water under extreme pressure, a hidden ocean that scientists believe may extend for thousands of kilometers, trapped inside a gas giant, never having seen sunlight, existing in conditions that challenge every assumption we make about where water can exist. Then the temperature climbs past the boiling point of every metal we use in spacecraft construction, then past the melting point, then into ranges that have no practical reference point in everyday engineering. The most significant and revealing data came from an unlikely source. In 1995, NASA deliberately sent the Galileo atmospheric probe, a specially built descent vehicle, into Jupiter's atmosphere. It was not designed to survive indefinitely. It was designed to gather as much data as possible before Jupiter destroyed it, which happened approximately 57 minutes after entry and roughly 200 kilometers below the cloud tops. In those 57 minutes, it recorded data that scientists are still analyzing today. It recorded wind speeds that increased with depth rather than decreasing, which overturned existing models of how gas giant atmospheres behave. It detected lightning, massive, continuous electrical discharges occurring throughout the atmosphere on a scale thousands of times more energetic than any lightning strike ever recorded on Earth. And then it went silent, crushed by pressure, consumed by heat, gone. Juno has since extended our understanding dramatically. Its microwave radiometer has allowed scientists to peer through the cloud layers and map Jupiter's internal structure with a level of detail never previously achieved. What it revealed shocked the science community. Jupiter's atmosphere is not a relatively thin shell sitting above a distinct interior. The atmospheric dynamics, the storms, the jets, the bands, extend downward for thousands of kilometers, far deeper than any model had predicted. The boundary between what we would call atmosphere and what we would call interior is not a clean line. It is a gradual, continuous transition into conditions that become progressively more alien with every kilometer of depth. But here is where the scientific picture becomes genuinely uncertain, and that uncertainty is important. For decades, the standard model of Jupiter's interior described a relatively clear sequence: gas atmosphere transitioning to liquid hydrogen, then to metallic hydrogen, and finally to a small, dense, rocky core at the center. Juno's gravity measurements have challenged that model in a significant way. The data suggests Jupiter may not have a distinct solid core at all. Instead, it appears to have what scientists are calling a diffuse or fuzzy core, a region where rocky and icy material is not compacted into a solid sphere, but is instead dissolved and mixed throughout a vast region of super-dense fluid. This means the boundary we expected to find simply does not exist in the way we thought, and that raises a question scientists are actively debating. If Jupiter formed differently than our models predicted, what does that mean for our understanding of how the entire solar system formed? The answer to that question has implications that extend to every planet, including Earth. The deeper you fall into Jupiter, the more the physics of our everyday world simply stops applying. Approximately 20,000 kilometers below the cloud tops, pressure reaches a point where hydrogen, the most common element in the universe, a gas in normal conditions, undergoes a phase transition into something that has no equivalent in everyday experience. It becomes metallic hydrogen. In this state, hydrogen atoms are compressed so tightly that their electrons are no longer bound to individual atoms. They move through the material the way electrons move through copper wire. Metallic hydrogen conducts electricity. It flows like a liquid but carries electrical current like a metal, and its motion driven by Jupiter's rapid rotation, the planet completes one full rotation in 10 hours, generates the most powerful magnetic field of any planet in the solar system. Jupiter's magnetic field is 20,000 times stronger than Earth's. It extends millions of kilometers into space, past the orbit of Saturn. It traps charged particles in radiation belts so intense that unshielded exposure near Jupiter's cloud tops would deliver a lethal radiation dose to a human being in under a minute. For humanity, Jupiter represents something beyond just a scientific challenge. It represents a fundamental boundary of what exploration can mean. Every mission we have ever sent to the outer solar system has had to account for Jupiter's gravity, Jupiter's radiation, and Jupiter's influence on the orbital dynamics of everything around it. The next generation of deep space missions, including potential crewed missions to the Jovian moons, will have to navigate the electromagnetic environment that Jupiter's metallic hydrogen interior creates. Engineers designing those missions are working with models built on data that Galileo and Juno collected by going as far into Jupiter as technology allowed. The hell that exists inside Jupiter is not just a dramatic description, it is the engineering constraint that defines the boundary of human reach into the outer solar system. Pull back even further, and Jupiter becomes something more than a planet.
It becomes a data point in one of the most important questions in modern astronomy. How common are gas giants, and what role do they play in making planetary systems habitable? We have now confirmed thousands of exoplanets orbiting other stars, and gas giants appear in a wide range of configurations, some orbiting extremely close to their stars, some in highly eccentric orbits that would destabilize inner rocky planets. Our solar system, with Jupiter sitting in a relatively stable orbit that shields the inner planets without disrupting them, may be rarer than we once assumed. Jupiter's internal conditions, the metallic hydrogen, the diffuse core, the magnetic dynamo, are replicated in various forms in gas giants across the galaxy. Understanding what falls into Jupiter, what survives, what is transformed, and what is simply erased tells us something about the physics of a category of world that may be among the most common in the universe. So the next time you see Jupiter rising in the east, steady and bright and seemingly peaceful, consider what is happening beneath that deceptively calm surface right now. Winds faster than anything on Earth are tearing through ammonia clouds. Lightning bolts the size of continents are flashing in the dark. Hydrogen is being crushed into a metal that should not exist.